Okay, we're back for our second set of notes for Chapter 4. We left off last time talking about precipitates and precipitation of lead iodide, and this is the slide, I think, where I left you. So we'll pick up there. We're going to try to get all the way through two, rather, redox reactions right now. So we're going to talk about acids and bases, but at any rate, solubility. Solubility is going to be the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. That's a really wordy way to say how much of something can we dissolve in, a liquid or a water or something like that. And so here it gives you an example of some soluble compounds, things from your book, some insoluble compounds, not something that I think you would need to memorize. But why is an insoluble compound important? Well, here you can see some examples of insoluble compounds. And you can tell what makes them insoluble is that each of them is residing separate from the liquid that it was placed in. And so it doesn't matter how much you stir or mix these things, they're really not going to dissolve, or at least stay dissolved in that liquid. And that is important to know. So there's their examples, their molecular formulas there. So, writing net ionic equations, we kind of talked about this a little bit with the spectator ions. So what you want to do is you write your balanced molecular equation, then you write the ionic equation that shows the electrolytes that have dissociated. Cancel out your spectator ions, and then you make sure the charges are balanced, number of atoms are balanced. We do have to be respectful of that law of conservation of mass when we balance our equations. And so here they're asking us to do silver nitrate with sodium chloride. And so then we'd have to write out what those are. So silver nitrate, Ag from your periodic table, and then NO3 is the nitrate ion, and then sodium chloride is just kind of table salt. And so basically what you want to do here is you want to split these up and say if Ag is positively charged, silver will be attracted to the negatively charged chlorine, and the positively charged sodium would be attracted to the negatively charged nitrate ion. So really all we're doing is like what you might call a double replacement or double displacement reaction. It's really not too bad. So here they wrote them as let's split Ag and the nitrate up, let's split Na and the chlorine up, and they left the solid together because it's a solid, and they split up the ions on the aqueous side. And so then of course we have our spectator ions. What's just sitting around? Well, we have sodium and nitrate that are just spectators. And so when we're focused on the precipitate, it's really not that surprising that the ions that we're left with in our net ionic equation are the ions forming the precipitate. So there it is, the net ionic equation. Okay, so why does this whole precipitate business matter? For a variety of reasons. One of them is the example given in your book, an undesirable precipitation reaction is calcium. You'll find all sorts of ions in just hard water, especially where we live here in the Midwest. Our water is relatively hard, so you're going to find these kinds of dissolved ions. So you have the calcium aqueous, so it means it's dissolved in water, plus another ion like a bicarbonate or something like that. I don't know what it is, sorry. Dissolved in water, and it's going to give us a calcium carbonate solid and a CO2 aqueous and H2O liquid. And that's fine because the aqueous CO2 is going to pass through the boiler, the liquid water is going to pass through the boiler, but this solid here you might recognize as calcium carbonate. This is like the solid that makes up eggshells. So what you get is this really nasty hard coating of calcium carbonate. So it's going to clog up the boiler, and that's of course very dangerous. The good news about it is it's not an impossible problem to solve, because if you've taken biology with me, you might remember dissolving the eggshell off of an egg with a weak acid, really with vinegar. So you can just add some acid to this and you can get rid of that. So it's not a huge deal, but if it goes unnoticed, then it's rather dangerous. So let's switch gears here just a little bit to acids and bases. I hope that some of this is review. We'll talk about Lewis in class because they just start with, I think, Bronsted or something Arrhenius. So anyways, acids in general have a sour taste. You can think of citrus fruits, being relatively acidic. Vinegar, of course, has acetic acid. It doesn't taste very good. Citrus fruits, citric acid, that kind of stuff. They do cause color change in some plant dyes, and they react with metals to produce hydrogen gas. Magnesium ribbon in hydrochloric acid is a really easy one to see. Little bubbles coming up, and those bubbles are hydrogen gas. Oh, look at that. Hey, that's what they use. Cool. So it's hydrochloric acid and magnesium. I guess it's such a cheap, easy demonstration that everybody relies on it. It gives us this magnesium chloride and then the hydrogen gas. It's real easy. We can do it in class. It takes like 2 minutes. So what do we have? They'll react with carbonates and bicarbonates to give us some carbon dioxide gas. And here's a picture. You can see all these bubbles in the top. That's the carbon dioxide gas that's being given off. So there we have it, hydrochloric acid, calcium carbonate. So this would be what we just talked about with the boiler or the eggshell. You know, you take your acid, you take your calcium carbonate, and the calcium chloride are going to form into this aqueous compound here, and then we'll give off CO2 gas after that. So aqueous acidic solutions conduct electricity. That shouldn't come as too much of a surprise to you because, like we've already mentioned, you know, if you look at the label on a car battery, it'll say, you know, caution contains acid, or it'll give you a little diagram of the corroding hand or something like that. So if we switch to bases, if you taste a base, which we generally don't taste things in the lab, they're going to have kind of a bitter taste. They feel slippery. A lot of the soaps that we use contain bases. Lye or NaOH is used in the production of a lot of soaps. It causes color changes in plant dyes. Its aqueous solutions also conduct electricity because, like we said before, you know, all we really need are some charged ions or electrolytes. And if an acid gives up hydrogens, great, it'll conduct electricity. If a base gives up OH minus, great, it'll conduct electricity. So examples, NH3 would work as a base and OH minus would work as a base. Both of these have the capacity to combine with another hydrogen, and that's going to help them act like a base. So we're going to look at a few different definitions of acids and bases. We'll start with Arrhenius. So here's an example of an Arrhenius acid, sorry. So an Arrhenius acid is a substance that produces hydrogen, and they put in parentheses here hydronium. The reason they do that is because most of our acid-base reactions are going to occur in a aqueous solution in water. And when you release hydrogen in water, it doesn't just float around as free, unbound hydrogen. It's going to immediately find water, bond to that water, and give us H3O. And so really, as we look at acids in this chapter, you can think to yourself that the concentration of hydrogen ions and the concentration of hydronium ions, we're basically saying the same thing there. So here we have hydrochloric acid with our little hydrogen and our large chlorine, and being an acid, it's going to give up its hydrogen. So who's it giving it to? Water, H2O. And so here this hydrogen is going to come and bond with the electrons here on the other side of this oxygen, and that gives us this H3O or hydronium and our free Cl minus. So what's an Arrhenius base? Well, if an Arrhenius acid produces hydrogen, an Arrhenius base produces OH minus. When in doubt, make water, right? And here we are with H and OH, what we need to make water. So NH3 is going to react with water, and you can see here that the water is giving up a hydrogen to the NH3, and that's becoming NH4. And so when it's NH4, it has acted as an Arrhenius base. Oops, shoot, I'm sorry, I said that wrong. That would be acting like a Lewis base. The water produced OH, so the water is actually the Arrhenius base. Sorry about that. Substance that produces OH minus in water. So the water is the Arrhenius base. I apologize for that. I've got Lewis kind of stuck in my head because we're skipping it. Okay, so hydronium ion, a hydrated proton. So the proton is just the H plus that we're letting go, and then hydrated means adding water, and so it's just oxygen with 3 hydrogens around it. Here you see the positive end and the negative end in this kind of space filling diagram. Okay, so now we're going to Bronsted. So a Bronsted acid donates a proton. A Bronsted base accepts a proton. So what do we have here? We have, again, NH3, again, H2O. And so if a Bronsted acid has to donate a proton, then it needs to give up its H plus. And so then here our water is giving up one of its hydrogens to the NH3. And so that makes the water act as a Bronsted acid. And so then the Bronsted base would be NH3 because it has accepted the proton. So there's the acid, there's the base, there's the acid, there's the base. Okay, so a Bronsted acid must contain at least one ionizable proton. Well, of course, because if an acid donates a proton, then if you don't have any protons, you can't very well act as that acid. So look for things with excess hydrogen. They're probably going to be your acid. NH3 is kind of our exception there. So monoprotic acids, pretty basic to break down. Mono is one. Prot would be proton. So a monoprotic acid is going to be some sort of molecular compound that only has one hydrogen that it can really give away. Hydrochloric acid would be monoprotic. It's a strong electrolyte, therefore a strong acid. Here, HNO3 only has one hydrogen to give away, monoprotic. Strong electrolyte, strong acid. Here we've got CH3COOH, only gives up one hydrogen. It's a little weaker electrolyte and a little weaker acid. And so diprotic acid, of course, if mono is 1, then di would be 2. H2SO4 can go through kind of a two-step process where in the first step it gives away one hydrogen and becomes HSO4. Then in the next step it can become HSO4, which gives up another hydrogen and becomes SO4 minus. So that from here in the very beginning all the way to just SO4 minus, that process is acting like a diprotic acid. You'll note, of course, they are a little different. The first version, H2SO4, is the strong acid, but after it's given up one of those hydrogens, it has that negative charge, and you can think it doesn't really want to become more negative. That's just a little bit less energetically favorable, so it's a weaker acid when it's at the HSO4 state as opposed to the sulfuric acid, H2SO4. So then there's triprotic acids, which of course you're getting the trend by now. This would be 3 hydrogens. So this I think is phosphoric acid, and it could give up one hydrogen and become H2PO4, and then it can do it again and become HPO4, and then it can do it again and become just PO4 3 minus. And you see here, weak electrolyte, weak acid, weak electrolyte, weak acid, because each time we give up a hydrogen, we become more and more negatively charged. And we'll learn later that with oxidation numbers, we really want to be about as neutral as we can. That's the most energetically favorable. So every hydrogen it gives up, it becomes just a little less energetically favorable. So not exactly what we want to do, but it will do it. It's just weak. It doesn't give them up readily. So. Some common strong and weak acids. So your strong acids, chloro, bromo, fluoroiodo, those kind of halogen groups there for you. Nitric, sulfuric, perchloric. Sulfuric, I'm pretty sure, is what's in our car batteries. And then some weaker acids, hydrofluoric acid, nitrous acid, phosphoric acid, and acetic acid in vinegar. So let's keep going here. So identify the following species as Bronsted, acid, base, or both. So you have to look back to figure out what your definition would be for Bronsted. And you'll see here, this is going to work as a Bronsted acid. It's giving up that hydrogen. Here we've got something accepting a proton. Okay, so that would be a Bronsted base. It's accepted that hydrogen. Here we've got one giving up a hydrogen. And so if it's giving up a hydrogen, pretty safe to guess acid. And then here we've got one accepting a hydrogen, so probably going to be a base. Okay, so a neutralization reaction is really not too bad. Basically, you take an acid and react it with a base, and it should give you a salt and a water. The water is really not going to change much, but the salt will vary depending on the acids and bases that you use. So here's really your most basic one, HCl. It's in like toilet bowl cleaner and that kind of stuff. Hydrochloric acid plus sodium hydroxide, which is lye. It's found in drain cleaner, and you can combine these two, and again, your positively charged sodium will be attracted to the negatively charged chlorine. When in doubt, make water. Here's the hydrogen going to the OH, making water, and we find ourselves making salt water, which is kind of cool considering the nasty substances that we're starting with, what we can get is really just salt water. So if you want to write your net ionic equation, absolutely do. Split your hydrogen into its ion, split your chlorine into its ion. Sodium and hydroxide do the same thing. Keep your OH together though. OH minus is its own ion. NaCl split up, water stays together, and then cancel your spectator ions. And then what you find is we're making water. So neutralization reaction with a weak electrolyte. So here's HCN, NaOH, and we're making NaCN and water. And so a weak acid plus a base will still give us a salt and a water. And so here they've split the sodium hydroxide because it's strong into its individual ions, but because it's a weak acid, sort of by definition, a weak acid is less likely to give up the hydrogen, as opposed to a really strong acid like hydrochloric readily gives up its hydrogen. And so that hydrogen is going to be a little more stubborn, but still, your Na will be attracted to that cyanide, the CN, and here we've canceled our spectator ions of the sodium, and we've got HCN kind of stuck together, OH, CN minus, H2O, and that's pretty much the end of that. So we'll still get that salt, we'll still get that water, but it's really probably not going to happen as quickly as it would with the strong acid. So what do we got? Neutralization, producing a gas. So some of them are going to give us a salt and a water and a CO2. Here you can see this with some sodium carbonate, some hydrochloric acid, giving us sodium chloride, a water, and CO2 kind of left over. Do make sure they're balanced. Here's the ionic equation for it. We split the hydrochloric acid into two parts. Note that they carried that coefficient of 2 down to each of the ions. They split sodium carbonate apart, and here they just put the 2 that was the subscript as the coefficient for sodium. So you're still having the same thing. Just don't be confused by that transition there. Sodium chloride, again, they split up, but they kept water and CO2 together. Okay, and then we've canceled out our spectator ions, and we have our net ionic equation for how to make water out of just the acid and base components. Okay, so with that, we start redox, and that will be a different video. So thank you. Sorry for the couple of errors there. Hopefully I'll get better as I continue to make these videos. That's all I've got for you right